Welcome to the presentation of Laridae. We're excited to share our tool with you, but first, some introductions are in order. I'm Stephanie, and my teammates, who you will be hearing from later in the presentation, are Mai and James. In today's presentation, we'll take you into the world of database schema migrations. We will discuss what database schema migrations are, why we would need to make changes, and their challenges. We'll then talk about strategies to mitigate these obstacles before diving into the core of Laridae and how it's integrated into a pipeline. So let's begin. What is Laridae? Well, it's a zero downtime, reversible database schema migration tool for Postgres, integrated into a deployment pipeline hosted on GitHub Actions. But what does any of that even mean? To better explain, we must first talk about database schemas. The schema is the structure of a database. This structure is defined by things such as the names of tables and table columns, data types of those columns, and any constraints that they may have. So recall, Laridae is a schema migration tool. Schema migrations are changes to the structure of the database, such as adding a column, changing a column's data type, adding a new table, etc. So Laridae is used to implement these kinds of changes. Okay, so now you might be wondering, why would we ever need to change the schema? Well, there are a number of reasons why someone would want to make changes. Some of the more common, adding a new feature, normalization, or even tuning queries to be more efficient. Most database schema changes are rarely an isolated task, however. Applications often have databases, and if changes occur in one, changes often have to occur in the other. And this adds complexity to the schema migration process. A key question Laridae seeks to answer is how to ensure that the database and the application code changes occur harmoniously. So let's use an example to examine some of the challenges involved with this. Let's say our current application stores data in a Postgres server. The application reads customers' phone numbers from a table called phones, which stores phone numbers as type char10, meaning each number is a string of strictly 10 characters. Originally, only US phone numbers were being stored, but now phone numbers need to include the country code. One approach we could take is update our database to meet this new requirement. So we update our phone column to be type char11, which would make each number a string of strictly 11 characters. However, our application code expects a string without a country code, and it may rely on this assumption. For example, if it's under the impression that the first 3 digits are the phone number's area code. A single character addition to a single field could be enough to cause chaos. In the best case scenario, the application gets confused and does nothing. Worst case scenario, the application breaks. A different approach might be to update the application code first and then the database. So we would change the application to expect a string with a country code, but then the problem is now that the database hasn't been updated yet to store char11 phone numbers, and again fails to meet the app's expectations, potentially causing downtime. Now that we've gone over the example, what are some of the challenges we're seeing? Let's first discuss compatibility. As we saw in our example, throughout the entire migration process, both the database and the application code must align with each other's expectations. If our application code expects a string without a country code, then being returned anything else could cause bugs or even break the app. The same goes for the database. If they require a particular input to write to the database, then failing to do so can result in errors. It's crucial to ensure that changes in either the app or database do not break the functionality of the other. A second challenge is reversibility. In the event that something goes wrong during the migration process, the ability to revert to a prior functional state of data and code is essential. In our phone example, we changed the data type to char11 before updating the application code. If this change had broken our app, we would want to be able to revert back ASAP. A third challenge we want to discuss is availability. While we are making schema changes, we don't want to disrupt reads and writes from the application. Going back to our example, as we make this data type change, application users shouldn't even notice when the change happens. They should still be able to save or read saved phone numbers from the database without any perceivable delay. Our final challenge is standardized workflow. By default, schema changes are often handled as one-off alterations applied manually to the database. We believe there should be a standard where database and application changes are coordinated. As we saw in our example, sometimes the timing of a schema migration can be difficult to get right, and having a standardized workflow can help mitigate risk. As we saw, there's some tricky stuff hidden in what appears to be a fairly straightforward process, and it should come as no surprise that there are several strategies that attempt to solve some of the challenges associated with schema migrations. The ones we'll be discussing today are Big Bang, schema versioning, online schema changes, and expand and contract. First up is Big Bang. When faced with the need to implement database schema migrations, this is an obvious first approach. A Big Bang migration consists of taking the application down, performing the schema migration, updating the application during downtime, and then deploying a new version of the application. So what are the pros? The Big Bang strategy does address the compatibility challenge. Temporarily bringing down the application before migration and bringing up the new version only after the migration is complete ensures constant compatibility between the running code and the existing database. But the Big Bang strategy leaves a lot to be desired. Thankfully, we do have other options. Next up is schema versioning. Schema versioning tools require the user to create a migration script that specifies the schema change and how the relevant data should be transformed to fit in the new schema. The tools then modify the database based on that script. So some pros for this strategy: the migration scripts are assigned versions and stored, thus providing a historical view of the database schema as it moves through time. This allows the database schema to be rolled back to an earlier version later, providing reversibility. But note, in some cases, there is no means of restoring lost data when reverting to these earlier versions. Another pro is tools that utilize this approach can also be integrated into deployment pipelines. Next, we have online schema changes. Online schema change tools modify a database schema without interrupting the database's regular operations by running a migration through simulation. So first, a ghost table is created. This is a new empty table with the same schema as the original table. Then the migration happens on this ghost table. The ghost table is then populated with original data from the original table via backfilling. Next, any newly written data from traffic is propagated to the ghost table. And then finally, once the migration is complete, the original table is swapped with the ghost table. So what are the pros? This process does allow the database to remain operational without interrupting users because the migration is happening on a separate table, thus addressing the availability challenge. It also addresses reversibility. These tools provide reversibility for a brief time frame immediately following the completion of the migration. During that window, the original table continues to be updated to facilitate quickly switching back to it if something goes wrong. Lastly, we have the expand and contract strategy. The expand and contract pattern, in essence, consists of 3 steps. Expand: the database is modified to tolerate old and new versions. Deploy: all the application instances are over time switched to the new version. And contract: the database is modified to work with only the new version of the application. So what are the pros? Expand and contract addresses the compatibility problem by shunting the difficulty onto the database. Essentially, different parts of the database satisfy the needs of each code version. This approach also addresses the challenge of reversibility. Until the contract step, everything the old code needs is still present, so the database changes can be undone without data loss. So now that we can see our options laid out, we can see that no single migration strategy addresses all four challenges. Each approach has pros and cons, and truthfully, depending on the use case, they are all viable options. Ultimately, we selected the expand and contract method as Laridae's underlying schema migration strategy. It was chosen for its ability to handle compatibility and reversibility obstacles, and our belief that expand and contract utilized with other implementation strategies can be used to resolve the availability and standardized workflow problems. And now my teammate Mai will take over and deep dive into the core of Laridae.
Thank you, Stephanie. Laridae was created to ensure this process happens seamlessly and at no availability cost to the application. Laridae also allows different versions of the application code to work on the same database simultaneously. And as we will see later, Laridae automates the deployment of database changes and application code changes in the correct order. To begin, let's see how expand and contract works out for our phone example. Recall that we are switching phone number from chart 10 to chart 11. For the expand phase, a new phone column is added to the existing table with the data type of chart 11. For the deployment phase, a new version of the application code, which requires 11-digit phone numbers, can be rolled out. This application version can use the new column for its functionality. Any instance of the application cluster is still running the older version can still safely use the old column with the 10-digit phone number. For the contract phase, when all the application instances are running the new code, the old number column can be safely dropped from the table without affecting application availability. There's a note that after the deployment step, but before the contract step, if we decide that we want to stick with a 10-digit phone number after all, the old version of the application can be easily redeployed and it should still work. So these are the steps that I previously talked about all in one picture. Of course, when we implement this, it will be a lot more nuanced than this picture is showing. So let's zoom into the expand step. We started out with just the original phone column. We need to add a new column, right? However, we obviously cannot name the new column number as well, because obviously columns need to have unique names within the same table. So we have to name the new column something different. Let's say we just name the new column new number with a data type of 11-digit. However, the problem now is that the developers on the application side should not have to worry about the new column's name. The new application should be able to just query the database as if the schema change has already been executed. So when the new application asks for the quote-unquote number column, data from the new number column should be returned instead. While the old application queries the database, it should still receive the original number data. Remember, the ultimate goal at the end of this process is that we can eventually drop this old column, withdraw the old application code, and just to clean up everything nicely, rename the new column to just be number. How are we going to do that? We're going to do it by using Postgres views and schemas. A view is a virtual table that combines columns from one or more underlying physical tables, potentially with some of them renamed. It can be read from and written to, just like a standard table. This leads to the next problem. How do applications specify which view should be used? So we use namespace schema to solve this problem. It's a namespace within a database that contains objects like tables, views, etc. Think of it like a directory that contains files. So multiple objects in a single database can have the same name if they exist in different namespace schema. So to apply views and schema to our phone number example, we can create two views. One only sees the old column and one only sees the new column. If an application is looking for a specific view, it can just query for the quote-unquote number column and be directed to the right physical column. We can then put the two views in two different namespace schema. Within each schema, the view can reference a table named employees and the number column contained within it. So far, we've added a new column and tell the different versions of the code where to go to find the column it needs, but we have not handled the existing data from the old column yet. At the current state, the new column has no data. This interferes with both application compatibility and availability. Even more so, incoming traffic will write more data into the table. Depending on from which application version the writes come from, only the corresponding column will contain the newly added data. We need to iron this process out by making sure data can transfer appropriately between the two columns. We solve that issue by doing backfilling and triggers. Backfill handles the existing data, and triggers handle incoming traffic data. When doing backfill, we go back and transfer data from the old column to the new column. We also need to transform this data so that they can fit the new column requirements. How the data is transformed depends on the use case. So for our specific phone example, we need to make sure to add a digit to the existing string so that it can be stored in the new char 11 column. Backfill might take a long time if there is a lot of existing data. Because of that, backfill will have to be done in batches in order to preserve the application availability. For newly added data, we use triggers that happens automatically in response to specific operations on a table. Laridae's triggers go off on updates and inserts at row level. If the old version of the column was modified, the change is propagated to the new version and vice versa. Also, similar to backfill, data will have to be modified upon transferring so that it can fit the receiving column's requirement. Let's review one more time. So far, we've added a new column, set up current and future data to be transferred, and the new application code has to way to correctly see the right version of the database. However, in order to truly preserve the availability of the database and the application, we also need to consider a very important Postgres features, which is locking. Let's talk about Postgres locks. Well, locks are exactly what they sound like. They lock things in a Postgres table. Explicitly, locks can lock reads and or writes and or updates. Locks are used so that there cannot be conflicting operations on the same table. There exist multiple types of lock, each of which have a different scope, what it can lock and what it can tolerate. Each lock also has a list of other locks that it can either coexist with or are mutually exclusive in a transaction. Of all the locks, the access exclusive lock is the most restrictive. It is a table-level lock, and it conflicts with every other lock. It means that the table cannot be accessed even just for a simple read query. Laridae wants to achieve zero downtime. However, some essential operations will have to acquire the access exclusive lock no matter what we do, even for just a few milliseconds. Therefore, we decided that Laridae would strive to keep the amount of access exclusive lock time to a minimum, but never possible to be completely zero. Since a truly zero downtime migration is never possible, we would have to formally define what we consider a quote-unquote zero downtime. To be more explicit, we need to decide on how much of a delay we can tolerate and still not interfering with traffic. There is no strict standard to define this time amount. Most companies have internal guidelines to define this, and from our research, we conservatively decided to define a zero downtime as 2 seconds or less of access exclusive lock time. How does Laridae manage to meet our definition of zero downtime? We employ various techniques with the migrations that we support to reduce access exclusive time. We describe these techniques in a lot more details in our complete write-up, and we will surely get the write-up at the end of the presentation. But due to time constraint, we will only have time to go into depth about one strategy. So let's talk about how we configure lock acquisition with lock timeout. Before talking about how lock timeout works, I'd like to show you how locks work in just a normal scenario. So in order to quickly explain things because of nation instead, hopefully it will make it easier to understand. This is you. Imagine you are at a checkout line at Walmart. Here, there are people in queue with you, and you're lining up to come to cashier number 2. Now, let's say you go to the front of the line, and it's your turn to interact with the cashier. She scans all of your items. Then maybe because she is a new employee and needs extra help, or because you bought something suspicious that needs double checking, she calls for a manager. The manager arrives and finishes your transaction. The cashier gives you your receipt, and you are free to go. The manager leaves the cashier to continue checking out the next person in line. In this example, you, the customer, is a SQL statement or transaction. The cashier is a Postgres process that was spun up per connection in order to execute queries. SQL queries are waiting in queue, waiting for its turn to be processed. Some statement require a lock to be obtained before the query can be executed. The manager represents the lock in this case. Now let's consider another scenario. Similar to before, you were waiting in line and you go to the front of the line that the cashier can't scan your item and then she calls for a manager. However, this time, the manager is helping cashier number 1 at a different checkout line. There's only one manager on duty. So now you and cashier number 2 are just waiting until the manager finishes whatever he was doing before he could come over to you. And for all you know, line 1 might need serious help that would require the manager to be occupied for a long time. This means that your entire checkout line has come to a stop. You're unable to finish your transaction, and no one behind you in line can move the line. Even though maybe the person next to you were only buying like one non-suspicious item that would not require the manager's input, they're stuck there with you anyway because you're holding up the line. Again, replacing the customer with SQL statement, the cashier is with a Postgres process, and then manager with the required lock. We can see how lock acquisition can slow down database performance and affect availability. Instead, a more efficient way to handle the situation would be for you to leave the checkout line. This allows for the cashier to work with the next customer in line and move the queue along. You can rejoin the checkout queue and hope that the next time you get to the front of the line that the manager will be available by then. This is essentially how lock timeout works. When a query requires a lock timeout makes sure that it only remains waiting for a set amount of time. When this time passes, the query leaves the queue, allowing for other queries to be executed. After another explicitly stated wait time has passed, the SQL can rejoin the queue and the process resume as normal. With that, I conclude our discussion about Laridae's core database functionality. Laridae, unlike other solutions on the market, comes with plug-and-play integration into GitHub Actions CI/CD pipeline. And now I will turn over to James to tell you more about this feature.
Thanks, Mai. So we've talked about how Laridae automates the expand and contract method to help make database migrations simpler and safer. We also talked about how we worked with Postgres's locks to achieve zero downtime migrations. Next, we'll discuss how this schema migration functionality can be synchronized with application deployments. Before we do, though, we need to talk about how app deployments are typically handled in modern companies. CI/CD, which stands for continuous integration and continuous deployment, is a widely used practice for deploying new application versions in a standardized and controlled fashion. It involves setting up automated processes that test and deploy new code once they are merged into a repo. The overall flow is as follows. First, developers merge code into their repository's main branch. Next, a build process is automatically started, transforming the code into a form that can be run by installing libraries, compiling, creating container images, etc. The results of the previous step are then tested with an automated test suite, and if the test passed, the code is deployed either to a staging area or straight to customers. How could Laridae be used in an environment like this? If we just offered Laridae as a command line tool, we'd run into two big problems. First, if new code required a schema change, Laridae would have to be run manually before it was deployed to expand the schema and afterwards to contract it. This turns the automated pipeline into an error-prone manual process. Second, most engineers might not even have direct access to the production database if it contains sensitive customer information, so deploying schema changes might require intervention from DevOps personnel. Because of these issues, we opted for a different approach. Laridae offers steps for expanding and contracting the database that can be slotted into an existing deployment pipeline. This way, performing Laridae's reversible zero downtime schema changes becomes as easy as updating application code. In order to achieve this integration, we had to narrow our use case. So we currently support deployment pipelines on GitHub Actions for AWS Fargate deployments. GitHub Actions is a popular CI/CD platform which allows developers to set up automated sequences of events that occur in response to changes in GitHub repos. A GitHub Actions workflow specifies what events, such as pushes, releases, or forks, to listen for, and what to do when those events occur. The steps in a workflow can be individual shell commands or existing actions from the GitHub Actions marketplace. The machine that runs a workflow is called a runner, and runners can be self-hosted or hosted by GitHub. As for AWS Fargate, it's a service for deploying containerized applications that's frequently used for APIs. Here's a diagram showing a deployment of an AWS Fargate app with a database, which is the infrastructure Laridae expects the client to have in place before it's added. The app and the database are in a private subnet, which is essentially just the cloud version of a private network. Neither has a public IP, but HTTP requests reach the app by first flowing through the load balancer in the public subnet, which does have a public IP. Now that we've explained the specific services we integrate with, how is Laridae actually used? To use Laridae, you update your existing GitHub Actions workflow by adding in Laridae's expand and contract actions which are available in the GitHub Actions marketplace. As we mentioned earlier, a typical CI/CD workflow runs in response to new code being merged into the main branch of a repo. To use our actions, if the user is merging code that expects an updated database schema, they include a migration script in the commit that specifies the necessary schema change. The expand action then uses that migration script to expand the database to tolerate new code expecting the new schema. It also adjusts the new application's database URL to reference the new schema. The contract action similarly contracts the user's database to only present the new schema. So the intended use case is for a developer to sandwich their existing deployment between the expand and contract steps so that the database can handle the new code by the time it's deployed, and no new code is still deployed when the database contracts. Offering these insertable pipeline steps came with some challenges, one of which we will now briefly describe. As we mentioned before, GitHub Actions execute on runners, machines that are either self-hosted or hosted by GitHub. Looking at the diagram of the user's AWS infrastructure we saw a couple minutes ago, we can see a problem for Laridae. To perform automated expand and contract, our script needs to connect to the user's database, which doesn't have a public IP. This means the runner itself can't just connect directly to the database and perform the migration. How then can the runner modify the user's database? We considered several solutions to this problem, but ultimately settled on the following approach. The GitHub runner uses the AWS command line interface to spin up a Fargate task in the user's VPC to perform, which in turn performs the migration. Fargate, which we briefly mentioned a few minutes ago, is a serverless computing engine for containers. So during Laridae's initialization process, we create an IAM user for the GitHub runner to assume with access limited to the required services. Let's summarize where we've been. Database schema migrations are a challenging process. However, as we've seen, with the right approach, the difficulty can be kept to a minimum. Laridae automates the expand and contract process to keep the complexity during a migration out of the code, so developers can worry about new features rather than preserving compatibility. Laridae also helps remove risk from migrations by allowing rolling back to a functional state of data and code, and works with locks to avoid application downtime. Finally, it synchronizes the streamlined schema migration process with app deployments by integrating it into a CI/CD workflow. So let's see what Laridae looks like in action. We'll show a simple example, updating a to-do app so that to-dos can be in 3 states, not started, partially done, or done, rather than just 2. So the underlying change to the database is changing the data type of a column called done from Boolean to text. So first, Laridae is initialized so it can access the user's AWS resources. The access key is transferred to the GitHub runner through a secret in your GitHub repo. So now we see the original form of the database with a Boolean done column. So now the user is merging a pull request, which includes the new code and a migration script specifying the schema change. So the GitHub workflow is now running Laridae to expand their database, and now we'll see the updated database schema with columns for both versions. So now their new code is deployed, and we'll see in a second both application versions side by side. So we see both versions at once and how changes that one makes are propagated to the other one. So again, these are both using the same database, even though they expect different schemas. So finally, the database is contracted to only tolerate the new schema. And we see the final form of the database with a text done column. Okay, thank you very much. We'll open it up for questions.
Looks like I have one question. Why did we use Fargate rather than something like Lambda, which seems like a more obvious choice? So I guess I can go ahead and answer that as well. So ultimately, we chose to go with Fargate instead of Lambda because Lambda does have a execution time limit on their processes. They cap it at 15 minutes. And so we thought rather than try to string together a bunch of Lambda processes together to instead pivot and use Fargate. Any other questions? Here's one question. Any particular reason we chose Postgres instead of MySQL?
Um, I can take that question. So Postgres is more performative than MySQL, even though MySQL has a larger legacy user base. As the saying goes, elephants are stronger than dolphins. And Postgres is a lot more predictable than MySQL. A lot of the things that we do for Postgres can be transferred to MySQL just fine, including all the lock timeout and all that. The locks work a little different for MySQL, but the general idea is the same. One other really important consideration that why we picked Postgres is because Postgres is more perceptive to open source projects like ours, as opposed to MySQL, which has a strong preference for enterprise tools instead. So the open source community is a lot more vibrant for Postgres.
Any other questions?
We have another question here. Were there any other types of optimizations you made to your SQL codes, Postgres configs, more worker processes, more client connection, etc.? Not for Postgres configs. So for the processes is going to be spun up per client connections. However, we did optimize all of the operations that we support, we optimize. So we're currently support 8, I believe is 8, either 8 or 9 operations. And we do have to break them up into chunks so that they don't take up a big chunk of the process time. We do have to use some tricks with them, like if you're doing an add not null constraint or adding a check constraint or create an index, we have to break them up into creating the constraint and then validating them separately so that the access exclusive lock was never obtained. It might take a little longer, but your trade-off is your percentage of time of being locked is significantly lower. I think we load test on a 10 million rows Postgres table, and doing just a single statement without Laridae takes something like 15 or 16 seconds, whereas Laridae takes a little bit over 20 to 25 seconds, but the percentage of lock time is under 5%. So traffic would still be able to flow in during all that time.
Well, any other questions before we wrap this up?
And we do have, so the link you're seeing on the screen is our complete write-up. So if you would like to read more about what we did with Laridae, we did talk about it more there. And thank you so much for coming.
All right, this concludes our presentation. Thanks so much, everyone. Feel free to message us on Slack with any additional questions. And yeah, thank you again.